Antimatter, the mirror of existence, the complete deep dive. Part 1. The mirror that could destroy the world. Right now, at this very second, while you're watching this video, something incredible is happening inside your body. Every few minutes, one of the potassium atoms in your muscles, bones, or blood emits a particle that could theoretically destroy an entire city. This particle is a positron, an antiparticle, a tiny fragment of antimatter being born right inside you. You are a walking reactor producing the most dangerous substance in the universe. And here's what really blows your mind. If we could collect just 1 gram of antimatter, less than a paperclip weighs, and let it touch ordinary matter, the result would be an explosion equivalent to 20 kilotons of TNT. That's the power of the bomb dropped on Hiroshima. 1 gram, the size of a grain of rice. Energy capable of wiping an entire city off the face of the earth. But wait, if antimatter is so destructive, why are we still alive? Why don't our bodies explode every time a positron is born inside them? And this is where the real story begins. A story that will make you completely rethink everything you knew about the nature of reality. Antimatter isn't a figment of science fiction writers' imaginations. It's not a plot from a superhero movie. It's a reality confirmed by countless experiments, studied in the world's largest laboratories, and yet it remains one of the greatest mysteries of modern physics. Because the existence of antimatter poses a question that science still can't answer. Picture this for a moment. 14 billion years ago, at the moment of the Big Bang, the universe created equal amounts of matter and antimatter. Perfect balance. Symmetry worthy of the most perfect mathematical equation. Matter and antimatter should have met, annihilated each other, and turned the entire universe into pure energy, into light, into emptiness. But that didn't happen. Somehow, for a reason that physicists around the world still can't fully explain, matter won. 1 extra proton for every billion particle-antiparticle pairs. A tiny, microscopic violation of symmetry, and from this minuscule remainder, from this unimaginably small excess, absolutely everything we see around us was formed. All galaxies, all stars, all planets, all living beings. You, reading these lines right now. We are a byproduct of the greatest cosmic catastrophe in the history of existence. We are accidental survivors in the war between matter and antimatter. And here's what's truly frightening. We still don't know why we exist. The laws of physics, as far as we understand them, say that the universe should be empty, sterile, filled only with residual radiation from an ancient annihilation. But the laws of physics are clearly missing something. Somewhere in the very foundation of reality lies a mechanism we haven't discovered yet, a principle we haven't formulated yet, a mystery we're only beginning to unravel. Antimatter isn't just an exotic substance. It's the key to understanding why the universe exists at all in the form we know it. But let's step away from cosmic scales for a second and talk about something more tangible, about practical applications, about what antimatter is already doing for us right now. If you've ever had a PET scan, positron emission tomography, then you were injected with a radioactive compound that emits positrons, antimatter, straight into your blood. These positrons collided with electrons in your body, annihilated, emitted gamma rays, and those rays allowed doctors to see tumors, study the workings of your brain, diagnose diseases with precision unmatched by any other method. Antimatter is already saving lives, every day, in hospitals around the world. But that's just the beginning. Scientists and engineers dream of antimatter as the fuel of the future. Imagine a spacecraft powered by an antimatter engine, mass to energy conversion efficiency, practically 100%. No chemical fuel, no nuclear reaction comes even close to this level. With an antimatter engine, travel to the nearest stars stops being fantasy. It becomes a matter of engineering. But there's a problem. A huge, colossal problem. Producing antimatter is the most energy-intensive process known to humanity. CERN, the world's largest particle accelerator, has produced approximately 20 nanograms of antihydrogen throughout its entire history. 20 billionths of a gram, over decades of work, with energy expenditures that could power a small city. If we wanted to produce 1 gram of antimatter with current technology, it would cost approximately $60 quadrillion. 60,000 trillion. More than the entire world's GDP for 1,000 years. Antimatter is the most expensive substance in the universe. So expensive that even talking about its cost seems absurd. And yet scientists continue to study it, continue to produce it, continue to trap individual atoms of antihydrogen in magnetic traps and hold them there for minutes, hours, trying to unlock their secrets. Why? Because antimatter can tell us things no other substance can. Because in the difference between matter and antimatter lies the answer to a question philosophers have asked for millennia. Why is there something rather than nothing? This isn't a rhetorical question. It's a literal, physical question with a concrete answer that we haven't found yet. Now let's talk about what makes antimatter antimatter. What distinguishes a positron from an electron? What makes an antiproton a mirror reflection of an ordinary proton? At first glance, the answer seems simple. Charge. An electron has a negative charge. A positron has a positive one. A proton is positive. An antiproton is negative. But this is just the tip of the iceberg, because there are particles without charge, neutrons, and they also have antiparticles, antineutrons. What distinguishes them? The answer takes us into the depths of quantum mechanics, into a world where particles are described not just by mass and charge, but by a whole set of quantum numbers. Baryon number, lepton number, spin, isospin, strangeness, charm, beauty, truth. Yes, physicists really do call some particle properties by these names. An antiparticle is a particle in which all these quantum numbers have the opposite sign. All additive quantum numbers are inverted. It's like a mirror, but not an ordinary mirror reflecting space. It's a mirror reflecting the very essence of the particle, its quantum identity. And here we come to the strangest part, the most paradoxical. According to all the laws of physics we know, matter and antimatter should behave absolutely identically. The CPT theorem, one of the most fundamental theorems of quantum field theory, states that any physical process should look the same if you simultaneously replace all particles with antiparticles, reflect space as in a mirror, and reverse time. This means that an anti-universe, flowing backward in time and reflected in a mirror, should obey the same laws as ours. Antihydrogen atoms should emit light at the same frequencies as ordinary hydrogen. Anti-stars should burn just as brightly. Anti-galaxies should rotate at the same speeds. And in 2016, the ALPHA experiment at CERN first measured the spectrum of antihydrogen. The result? Identical to hydrogen, with precision down to 2 parts per trillion. Symmetry confirmed. Antimatter really is a perfect mirror reflection of matter. But then the question becomes even sharper. If they're so identical, if there's no difference in their behavior, why did one win and the other disappear? Why are we made of matter and not antimatter? Or, thinking even deeper, is there even a difference? Maybe somewhere in the universe there are entire galaxies made of antimatter, and their inhabitants call their atoms matter and ours antimatter. How would we know? This is the question that haunts physicists. If an anti-star burns exactly like a regular star, if an anti-galaxy looks exactly like a regular galaxy, how can we tell them apart from a distance? The light they emit is identical. The gravity they create is identical. At first glance, it seems impossible, but scientists found a way. Boundaries. If there were regions of antimatter in the universe, between them and regions of ordinary matter, there would have to be zones of annihilation. Cosmic border zones where matter and antimatter meet and turn into pure energy. These zones would glow with characteristic gamma radiation that can't be confused with anything else. And we don't see such zones anywhere in the entire observable universe. This means one of two things. Either antimatter is practically absent from the universe, and then we need to explain where it went, or it exists but is so far from ordinary matter that there's no contact between them, and then we need to explain how this separation happened. Both options require physics that goes beyond what we currently understand. Both options point to new laws of nature we haven't discovered yet. And that's exactly why antimatter remains one of the hottest topics in modern physics. Not because it can serve as a weapon or fuel, though it can, theoretically, but because in its existence, in its properties, in its mysterious disappearance from the early universe lie clues to new physics, to theories that will unify quantum mechanics and gravity, to understanding what happened in the first fractions of a second after the Big Bang. To answering a question that sounds almost metaphysical, but is actually strictly scientific. Why does the universe exist? Today we'll embark on a journey through the history of antimatter, from the first theoretical prediction, made through a brilliant mathematical trick, through experimental confirmations that shook the scientific world, to modern experiments that trap individual atoms of antimatter and study them with unprecedented precision. We'll learn how antimatter is born in thunderstorms and cosmic rays, how it's produced in particle accelerators and used in medicine, how scientists are trying to understand the greatest asymmetry in the history of the cosmos. We'll dive into quantum mechanics, relativistic physics, and cosmology, but I promise everything will be explained so that anyone can understand. No formulas without explanations, no dry recitation of facts. Only a captivating story full of unexpected twists, paradoxes, and discoveries. Get ready, we're starting. Part 2. The equation that predicted the impossible. 1928, Cambridge, England. A young physicist named Paul Dirac sits in his office, hunched over sheets of paper covered with equations. He's 25 years old, thin, withdrawn, almost pathologically uncommunicative. Colleagues joke that the unit of talkativeness, 1 Dirac, equals 1 word per hour. But what's happening in his head will forever change our understanding of the universe. Dirac is working on a problem that has tormented physicists for several years. Quantum mechanics and special relativity, the two greatest achievements of 20th century physics, refuse to work together. The Schrödinger equation, which describes the behavior of quantum particles, doesn't account for effects of motion at speeds close to the speed of light. And for electrons in atoms, especially in heavy atoms, these effects matter. A new equation is needed, an equation that will unite quantum mechanics with relativity. Dirac isn't the first to attempt this. Klein and Gordon already proposed their equation 2 years earlier. But it has a strange feature. It gives negative probabilities. And probability can't be negative. The probability of finding an electron at a certain point can't be minus 30%. That's nonsense. Dirac understands the problem. The Klein-Gordon equation is second order in time. It contains a second derivative with respect to time. But the Schrödinger equation is first order. To get the correct quantum interpretation, you need an equation that's first order in time but still compatible with relativity. Mathematically, this seems impossible. Relativity requires symmetry between space and time. If an equation is first order in time, it should be first order in spatial coordinates too. But how do you reconcile this with the relativistic relationship between energy, momentum, and mass? Dirac finds a solution. Elegant, unexpected, almost magical. He introduces a new mathematical object, 4x4 matrices. 4 rows, 4 columns, 16 components. These matrices, which would later be called Dirac's gamma matrices, allow you to write a first-order equation in both time and space while preserving relativistic invariance. The Dirac equation is born, and it's beautiful. It automatically describes the spin of the electron, the intrinsic angular momentum that was previously introduced artificially into theory as an additional hypothesis. The Dirac equation derives spin from first principles. This is one of those rare moments in the history of physics when mathematics itself tells you more about nature than you expected. But the equation has a feature, a strange, troubling feature. For every solution with positive energy, there's a corresponding solution with negative energy. An electron with energy -1 unit, -2 units, -1,000,000 units, an infinite ladder descending into the abyss of negative energies. This is a catastrophe, a physical catastrophe. Think about it this way. Imagine a ball sitting on a shelf. If there's a lower shelf available, the ball will eventually roll down to it. That's basic physics. Systems seek their lowest energy state. Now imagine there's not just one lower shelf, but an infinite number of them, going down forever. The ball should keep falling forever, releasing infinite energy as it goes. That's essentially what the Dirac equation was predicting for electrons. If states with infinitely negative energy exist, electrons should fall and fall, emitting infinite amounts of energy. All atoms in the universe should instantly collapse. Electrons should plunge into the abyss of negative energies, and the world should turn into a catastrophic flash of infinite energy. Obviously, this doesn't happen, but the Dirac equation claims it should. Dirac could have discarded his equation, admitted it was wrong, gone back to working on something else, but he doesn't, because the equation is too beautiful, too elegant, too good at describing the electron's spin. It has to be right. Which means those strange negative energy solutions need explaining. And in 1930, Dirac proposes a hypothesis that seems completely insane. He suggests that all negative energy states are already occupied. Vacuum, empty space that we consider empty, is actually filled with an infinite sea of negative energy electrons. These electrons are invisible because they're everywhere. We can't detect them directly because we have no reference point. It's like a fish that doesn't notice the water it swims in. Thanks to the Pauli exclusion principle, the rule that says two electrons can't occupy the same quantum state, ordinary electrons can't fall into these states. They're already taken. No room. Catastrophe averted. But this isn't the end of the story. It's only the beginning. Dirac continues reasoning. What if one of the electrons of the negative energy C receives enough energy, say by absorbing a very energetic photon? Then it could jump out of the C and become an ordinary positive energy electron, and a hole would remain in the C, an empty spot, the absence of an electron with negative energy and negative charge. Mathematically, the absence of a negative charge is equivalent to the presence of a positive charge. The absence of negative energy is equivalent to the presence of positive energy. The whole behaves like a particle with positive charge and positive energy, with the same mass as an electron, but with the opposite sign of charge, an anti-electron, a positron, a particle no one had ever observed, a particle that must exist if the Dirac equation is correct. At first, Dirac himself hesitates. The idea seems too bold. In 1930, he cautiously suggests that the whole might be a proton, a positively charged particle that was already known. Yes, a proton is 2,000 times heavier than an electron, but perhaps that could somehow be explained. Other physicists quickly point out the problem. Hermann Weyl and Robert Oppenheimer independently show that the whole must have the same mass as the electron. A proton doesn't fit. It has to be a new particle, a particle no one has ever seen. Dirac accepts the inevitable. In 1931, he publishes a paper openly predicting the existence of an anti-electron, a particle with the electron's mass and opposite charge. This is one of the boldest theoretical predictions in the history of physics. To predict the existence of a fundamentally new form of matter based solely on the mathematics of an equation. And just 1 year later, this prediction is confirmed. Carl Anderson, a young American physicist from the California Institute of Technology, is studying cosmic rays. He uses a cloud chamber, a device filled with supersaturated vapor in which charged particles leave visible tracks. A magnetic field curves the trajectories of particles, and from the curvature, you can determine the charge-to-mass ratio. On August 2, 1932, Anderson photographs a track he can't explain. The curvature indicates a particle with the mass of an electron. but the direction of curvature is wrong. If it were an electron, it should have been moving upward, but a lead plate the track crosses shows the particle was moving downward and lost energy when passing through the plate. This means the particle had a positive charge. A positively charged electron. Anderson names it the positron, the first antiparticle ever detected experimentally. Dirac was right. His equation was right. Mathematics had predicted reality. For this discovery, Dirac and Anderson would receive Nobel Prizes. Dirac in 1933 for creating quantum mechanics, Anderson in 1936 for discovering the positron. But the true significance of these discoveries goes far beyond 2 prizes. For the first time in the history of science, pure mathematics predicted the existence of a fundamentally new entity in nature. Not a modification of something known, not a refinement of parameters, but something entirely new. A whole new class of matter, a mirror reflection of everything we knew. This changed everything. It changed the very philosophy of physics. Mathematical beauty and symmetry ceased to be merely aesthetic criteria. They became guiding stars to new discoveries. If an equation is beautiful enough, elegant enough, perhaps it's true, even if its predictions seem crazy. Physicists would apply this lesson again and again. Quarks, gluons, the Higgs boson, gravitational waves, all were predicted theoretically long before experimental detection, and each time the predictions proved correct. But let's return to antimatter, because the discovery of the positron was only the beginning. If the electron has an antiparticle, it's logical to assume that other particles should have antiparticles too. The proton, the neutron, all the rest. In 1955, 23 years after the discovery of the positron, the antiproton was detected at the Bevatron Accelerator in Berkeley. Emilio Segre and Owen Chamberlain directed a beam of protons at a copper target with energy of 6 billion electron volts. Among the thousands of different particles born in the collisions, they found negatively charged particles with the mass of a proton. Antiprotons, mirror reflections of protons. A year later, in 1956, the anti-neutron was detected at the same facility. The neutron is electrically neutral. The anti-neutron is too. What distinguishes them? Quantum numbers. Baryon number. The neutron has baryon number +1. The anti-neutron has -1. By the end of the 1950s, physicists were certain every particle has its antiparticle. This isn't a peculiarity of electrons. It's a fundamental principle of nature, a symmetry pervading all that exists. But with symmetry came mystery, the very mystery we mentioned at the beginning. If matter and antimatter are born in pairs, and they are, this follows from conservation laws, then where did all the matter in the universe come from? Where's the corresponding antimatter? The Big Bang should have created equal amounts. Perfect symmetry. Then matter and antimatter should have met, annihilated, turned into photons, pure energy with nothing left over. But there is something left over. We are that something. What went wrong? Or rather, what went right so that we could exist? This question would haunt physics throughout the entire second half of the 20th century, and it remains relevant to this day. We know part of the answer. We know that the symmetry between matter and antimatter isn't perfect. There are tiny, barely noticeable differences. CP violation. We'll talk about this in detail later. But the known CP violation isn't enough. It's too small to explain the observed asymmetry. The difference is billions of times smaller than needed. Somewhere in physics, there's a gap. New physics, new phenomena, new particles, something we haven't discovered yet. and antimatter is our best tool for searching for this new physics. But before we dive into modern experiments and cosmological mysteries, let's make sure we fully understand the basic concepts. What exactly happens when matter meets antimatter? Why does annihilation release such monstrous energy? And why is this not just an explosion, but something much more fundamental? The answers to these questions will take us to the very heart of Einsteinian physics, to the famous formula that everyone knows but few truly understand. E equals mc squared. Energy equals mass times the speed of light squared. This formula isn't just an equation, it's a law of exchange, a law of equivalence. Mass and energy are the same thing, expressed in different units, like kilometers and miles, like kilograms and pounds, different ways to measure the same entity. When an electron meets a positron, they don't just explode, they disappear. Literally, their mass converts to energy. All of it, without remainder. 2 gamma photons fly off in opposite directions, carrying energy equal to the mass of the electron and positron. How much is that? Let's calculate. The mass of an electron is about 9 times 10 to the minus 31st power kilograms, negligibly small. The speed of light is 3 times 10 to the 8th power meters per second. The square of the speed of light is 9 times 10 to the 16th. Multiply. The energy of one electron is about 8 times 10 to the minus 14th joules. Still very small, but that's one electron. Now imagine a gram. In a gram of matter, there are roughly 10 to the 23rd power electrons and the same number of protons and neutrons. Multiply by the energy of each particle. You get approximately 90 trillion joules. 90 trillion joules from 1 gram. That's the energy of 20 kilotons of TNT, Hiroshima, from matter that would fit on the tip of your finger. To put this in perspective, if you could fully convert a single raisin into pure energy, you'd get roughly the same amount of power that a nuclear power plant produces in an entire day. This is why antimatter is so dangerous. This is why it's so attractive as an energy source. This is why scientists and military personnel around the world dream of harnessing it. But there's a catch. A huge catch. The law of conservation of energy doesn't go anywhere. To create antimatter, you need to expend at least as much energy as you'll get from its annihilation. In practice, much more, because the creation process is inefficient. Antimatter isn't a source of energy, it's a battery. A way to store energy in an incredibly compact form. You invest energy to create antimatter. Then you can extract that energy back during annihilation. For interstellar travel, this could be incredibly useful. You can't bring a fusion reactor with you, too heavy. You can't bring enough chemical fuel, even heavier. But if you could bring a few grams of antimatter in a magnetic trap, it's a dream. For now, just a dream. Because producing and storing antimatter is incredibly difficult. But we're getting ahead of ourselves. Before talking about the future, we need to understand the present. How do scientists study antimatter today? What have they already learned? And what mysteries remain unsolved? The journey continues, and the most interesting part is still ahead. Part 3. Hunters of the Invisible. How to trap antimatter. Imagine the problem. You need to catch a particle that is destroyed on contact with any substance. The walls of any container are made of matter. Air is made of matter. Your hands, your instruments, any detector you could use to register it. All of this is matter. As soon as an antiparticle touches anything, it instantly annihilates. A flash of gamma rays, and nothing. How do you catch something you can't touch? This isn't a philosophical puzzle. It's a real engineering problem that physicists solve every day in the world's largest laboratories. And they solved it. The solution is called a magnetic trap. Think back to high school physics. A charged particle moving in a magnetic field is deflected. The Lorentz force. This is the same force that made electron beams in old televisions deflect and draw images on the screen. The same force that curves particle tracks in detectors. If you configure the magnetic field correctly, you can make the particle move in a closed trajectory, in a circle, in a spiral, in a complex three-dimensional shape that never crosses the container walls. The particle hangs in emptiness, held by invisible forces. It touches nothing material. There's nothing for it to annihilate with. It can exist like this indefinitely. The first magnetic traps for antimatter were created in the 1950s. Simple configurations that held antiprotons for fractions of a second. But since then, the technology has come an enormous way. Today's traps use the most complex configurations of magnetic fields. Quadrupole traps, pinning traps, Yaffe-Pritchard traps. The names sound like spells from a dark arts textbook, but behind them lies precise physics and engineering. At CERN, on the border of Switzerland and France, several experiments specialize in antimatter. Alpha, Asakusa, A-trap, Base, G-bar, Aegis. Each attacks the antimatter puzzle from different angles. Let's start with how they even get antimatter for these experiments. It all begins with the antiproton decelerator, a unique facility that exists only at CERN. This is a machine that produces and slows down antiprotons. The process looks like this. Protons are accelerated to enormous energies in the proton synchrotron. Then they're directed at a metal target. During collision, some of the energy converts to mass. Pairs of particles and antiparticles are born. Among them, antiprotons. But these antiprotons are flying at speeds close to the speed of light. They can't be caught. They're too fast. So they need to be slowed down. The antiproton decelerator does exactly that. Using a complex system of magnets and electric fields, it slows antiprotons by trillions of times, from speeds close to light speed down to a few kilometers per second. That's still fast by human standards, but slow enough for experiments. Then the antiprotons are passed further, to the ELENA facility, the extremely low-energy antiproton ring. Here, they're slowed even more, down to meters per second, speeds comparable to a walking pedestrian. And only after this do the antiprotons reach the experiments, the magnetic traps, where they can be stored for minutes, hours, sometimes days. But antiprotons are only half the battle. To create antihydrogen, you also need positrons. Positrons are easier to obtain. Some radioactive isotopes, sodium-22 for example, decay by emitting positrons. You just take a piece of such material and collect the positrons that fly out. But they also need to be slowed down and cooled. Positrons from radioactive decay are too energetic for experiments. Cooling positrons is a separate art. They're directed into special traps where they lose energy by colliding with a buffer gas, nitrogen or neon. Each collision takes away some energy. The positrons gradually cool until they reach a temperature of a few kelvins, nearly absolute zero. Now we have cold, slow antiprotons and cold, slow positrons. The next step is to combine them into atoms of antihydrogen. This is harder than it sounds. The antiproton and positron must meet with the right relative velocity. Too fast, and they'll just fly past each other. Too slow, well, that's actually good, but it's hard to achieve. The alpha experiment uses what's called three-body recombination. Positrons and antiprotons are mixed in a dense cloud. Sometimes an antiproton flies past two positrons simultaneously. One positron is captured, the second carries away the excess energy. An antihydrogen atom is born. This happens extremely rarely. Out of millions of antiprotons and positrons, only a handful form antihydrogen atoms. But that's enough. In 2010, the alpha experiment succeeded not only in creating antihydrogen, but also in holding it in a trap. 38 atoms, held for almost 0.2 of a second. It seemed like a miracle. For the first time in history, antimatter was caught and kept long enough for study. Since then, records have been broken many times. In 2011, antihydrogen was held for more than 1,000 seconds, almost 17 minutes. In subsequent years, the count went to hours. But holding antimatter is half the battle. You also need to study it. What do scientists want to learn? The main question: Does antihydrogen behave the same as ordinary hydrogen? The CPT theorem says yes. If you take any physical process, replace particles with antiparticles, reflect space, and reverse time, the result should be identical. From this follows that the spectrum of antihydrogen, the frequencies of light it emits and absorbs, should be exactly the same as hydrogen's. Testing this prediction is one of the most important tests of fundamental physics. In 2016, the ALPHA experiment first measured the optical spectrum of antihydrogen. Scientists irradiated antihydrogen atoms with laser light of a specific frequency and watched whether they absorbed it. The result? Antihydrogen absorbs light at the same frequency as ordinary hydrogen, with precision down to 2 parts per trillion. That's stunning precision, and stunning confirmation of CPT symmetry. But scientists aren't stopping. They continue refining measurements, looking for the slightest deviations, because even a tiny deviation, 1 part in a quadrillion, would mean new physics, physics beyond the standard model. So far, no deviations have been found. Antimatter stubbornly behaves like a perfect mirror reflection of matter. But this isn't the only thing scientists want to learn. Another critical question: how does antimatter interact with gravity? Yes, you read that right. We don't know for certain whether antimatter falls down or up. Sounds crazy? Let's break it down. General relativity, our best theory of gravity, says that all forms of energy and mass attract each other. Antimatter has positive mass and positive energy, so it should be attracted to Earth and fall downward, just like ordinary matter. But we'd never tested this directly. Until recently, we simply didn't have the technical capability. The problem is that antiparticles are charged. The electric and magnetic forces acting on them are billions upon billions of times stronger than gravity. The slightest stray electric field would completely mask any gravitational effect. You need neutral antimatter atoms, antihydrogen, and you need a trap where you can study their fall. The G-bar experiment at CERN is working on exactly this. The idea? Create an antihydrogen ion, an antihydrogen atom with an extra positron. It's positively charged, easy to cool to ultra-low temperatures. Then use a laser to strip off the extra positron. You're left with a neutral, cold antihydrogen atom, and you can observe where it goes. In 2023, the ALPHA experiment first directly observed the gravitational behavior of antimatter. The result? Antihydrogen falls down, just like ordinary matter. Anti-gravity ruled out, at least in its simplest form. But the precision of this measurement is still limited. It's possible that antimatter falls slightly slower or slightly faster than ordinary matter. Experiments continue. Now let's talk about another aspect of antimatter, its existence in nature. We said that antimatter is produced in accelerators, but that's not the only place it's born. Antimatter is constantly being created around us, in space, in the atmosphere, even in our bodies. Cosmic rays, streams of high-energy particles coming from deep space, constantly bombard Earth's atmosphere. When a cosmic ray proton collides with an air atom's nucleus, a cascade occurs. Dozens, hundreds of secondary particles are born. Among them, positrons and antiprotons. These antiparticles don't live long. They quickly meet ordinary matter and annihilate. But at any given moment, billions of antiparticles exist in Earth's atmosphere. They're born and die in an endless cycle. Moreover, antimatter is born during thunderstorms. Yes, ordinary thunderstorms. Lightning is a powerful electrical discharge. Electrons are accelerated to enormous energies. When they collide with air atoms, they produce Bremsstrahlung, breaking radiation in the form of gamma rays. And if a gamma photon is energetic enough, it can create an electron-positron pair. In 2009, the Fermi satellite detected streams of positrons emanating from Earth's thunderstorms. Earth turned out to be a natural antimatter generator. Not a very efficient one, but constantly operating. And finally, your body. Potassium-40, a radioactive isotope, is present in all living organisms. It's necessary for nerve and muscle function, and it decays by emitting positrons. Every few minutes, one atom of potassium-40 in your body emits a positron. This positron travels a fraction of a millimeter, meets an electron, and annihilates. 2 gamma photons fly off in opposite directions, pass through your body, and escape into space. You are a source of antimatter, weak but constant. This process underlies PET scanning. A patient is injected with a compound containing a positron-emitting isotope. The isotope concentrates in certain tissues, tumors, active brain regions. Positrons annihilate. Gamma photons are registered by detectors. A computer reconstructs a 3-dimensional map of the compound's distribution in the body. Antimatter saves lives every day in thousands of hospitals around the world. But let's return to the big mystery, the question that haunts cosmologists. Why is there so little antimatter in the universe? We talked about this earlier, but let's dive deeper. Because this mystery is one of the deepest in modern physics. The Big Bang occurred 13.8 billion years ago. In the first moments, the universe was unimaginably hot. So hot that particles and antiparticles were constantly being born and annihilating. Electron-positron pairs, proton-antiproton pairs, neutron-antineutron pairs, all were in thermal equilibrium. As it expanded, the universe cooled. At some point, the temperature dropped enough that new pairs stopped being born. The remaining particles and antiparticles should have met and annihilated. If matter and antimatter had been exactly equal, the result would have been a universe filled only with photons, no galaxies, no stars, no planets, no us. But we exist. Galaxies exist. The universe is filled with matter. This means that at the beginning there was a small excess of matter over antimatter, approximately 1 extra proton for every billion proton-antiproton pairs. 1 in a billion, a tiny asymmetry, but it determined everything. Where did this asymmetry come from? In 1967, Soviet physicist Andrei Sakharov formulated 3 conditions necessary for the emergence of baryonic asymmetry. The excess of matter over antimatter. First condition, violation of baryon number conservation. There must exist a process in which the number of baryons, protons and neutrons, changes. Baryons must be able to be created or destroyed, not in pairs with antibaryons, but on their own. Second condition, violation of C-symmetry and CP symmetry. C-symmetry is symmetry between particles and antiparticles. CP symmetry is symmetry between particles and mirror-reflected antiparticles. If these symmetries are exact, any process creating an excess of matter will be compensated by a symmetric process creating an equal excess of antimatter. Third condition, departure from thermal equilibrium. In thermal equilibrium, all processes run in both directions at the same rate. Creation and destruction of baryons are balanced. For asymmetry to accumulate, equilibrium must be broken. These 3 Sakharov conditions are like a blueprint for creating a material universe. Any theory explaining baryonic asymmetry must include all 3 elements. And here's the puzzle. The standard model of particle physics, our best theory of the microworld, includes all 3 elements, but in insufficient amounts. Baryon number violation? Present. Theoretically, at very high temperatures, so-called Sphaleron processes can change baryon number. But these processes are too suppressed to create the observed asymmetry. CP symmetry violation? Present. Discovered in 1964 in neutral kaon decays. Nobel Prize in 1980. Later found in B meson decays. Nobel Prize in 2008. But the amount of CP violation in the standard model is too small. Billions of times smaller than needed. Departure from equilibrium? Present. Phase transitions in the early universe. But the transition in the standard model is too smooth, not sharp enough. The standard model cannot explain why we exist. This isn't a failure of the theory, it's a pointer to new physics. to something beyond the standard model, to new particles, new interactions, new sources of CP violation. And that's exactly why studying antimatter is so important. Every precise measurement of antiparticle properties is a search for tiny deviations that could point to this new physics. So far, we've found nothing. Antimatter stubbornly respects all known symmetries, but the search continues. And someday we may find the answer to why the universe exists. Part 4. CP violation, a crack in the mirror of the universe. 1956. Two young Chinese-American physicists, Tsung-Dao Lee and Chen-Ning Yang, publish a paper that shakes the physics world to its foundations. They propose the unthinkable. The fundamental laws of nature may not be symmetric under mirror reflection. Until this moment, physicists were absolutely certain. If you take any physical process and reflect it in a mirror, the result will obey the same laws. This is called p-symmetry, where p stands for parity. Think about it. A billiard ball rolling left appears to roll right in a mirror, but the laws of mechanics are the same for both cases. An atom emitting a photon to the left appears to emit a photon to the right in a mirror, but the laws of electrodynamics are the same. This seemed self-evident. How can the universe distinguish left from right? What makes one direction special? Lee and Yang noticed that for the weak nuclear interaction, the force responsible for radioactive decay, this symmetry had never been experimentally tested. Everyone just assumed it must hold. They proposed testing it. Qin-Sheng Wu, a brilliant experimentalist from Columbia University, took on this task. She cooled cobalt-60 nuclei to temperatures near absolute zero and aligned their spins in one direction using a magnetic field. Then she observed which direction the electrons flew out during beta decay. If p-symmetry held, electrons would fly out equally often up and down relative to the nuclear spin direction. A mirror reflection of the experiment would look exactly the same. The result stunned everyone. Electrons preferred flying in one direction. Nature distinguished left from right. P-symmetry was violated. This was in January 1957. In December of that same year, Lee and Yang received the Nobel Prize, one of the fastest transitions from discovery to award in history. But violation of p-symmetry was only the beginning. Physicists quickly noticed that you could combine p-symmetry with another symmetry, C-symmetry. C stands for charge conjugation. This is the operation of replacing all particles with antiparticles. The idea was elegant. Yes, p-symmetry is violated. Yes, C-symmetry is also violated. This was discovered soon after Wu's experiment. But perhaps the combination CP, simultaneously reflecting in a mirror and replacing particles with antiparticles, remains an exact symmetry. Think of it this way. An electron flying left breaks some rule, but a positron flying right breaks it in exactly the same way, in the opposite direction. Two violations cancel each other out. The overall picture is symmetric. It's like finding out that a coin is biased. It lands heads more often than tails. But then you discover that for every coin that favors heads, there's an anti-coin that favors tails by the same amount. The combined system is still fair. This would have been beautiful. This would have been logical. This would have explained why p-symmetry is violated, but the world is still orderly. And for several years, physicists believed that CP symmetry was exact. It became the new dogma. But in 1964, the world was again shaken by discovery. James Cronin and Val Fitch from Princeton University were studying decays of neutral kaons. A kaon is a meson, a particle consisting of a quark and an antiquark. The neutral kaon is special because it can transform into its antiparticle and back. Kaon becomes antikaon, antikaon becomes kaon. Quantum mechanics allows a particle to be a superposition of itself and its opposite. Because of this property, Neutral kaons exist in two forms with different lifetimes: short-lived K short and long-lived K long. K short decays into 2 pions. K long decays into 3 pions. If CP symmetry is exact, K long should never decay into 2 pions. This is forbidden by symmetry. Absolutely. Unconditionally. Cronin and Fitch discovered that roughly 1 in 500 K long decays produces 2 pions. CP symmetry is violated. This wasn't just the violation of yet another symmetry. This was the violation of the last hope for complete symmetry between matter and antimatter. This meant that the laws of physics actually distinguish between particles and antiparticles. Not strongly, not obviously, but they do. Cronin and Fitch received the Nobel Prize in 1980, but the significance of their discovery went far beyond particle physics. Remember the Sakharov conditions? To create baryonic asymmetry, you need CP violation. Here it is. Nature provided a mechanism allowing matter and antimatter to behave differently. A mechanism that could explain why matter won. But the joy was premature. Quantitative calculations showed CP violation in kaon decays is too small, many orders of magnitude smaller than needed to explain the observed baryonic asymmetry. The discovery of CP violation in B mesons in the early 2000s, the Babar and Bell experiments, Nobel Prize in 2008 to Kobayashi and Maskawa for the theoretical prediction, didn't change the picture. Yes, CP violation was found there too. Yes, it confirmed the mechanism predicted by the standard model, but the amount of CP violation remained too small. Here's a riddle within a riddle. We know that CP symmetry is violated. We know this is necessary for our existence. But the known violation isn't enough. There must be some other source of CP violation, some process, some particle we haven't yet discovered. This is one of the main motivations for building new accelerators, for conducting ever more precise experiments. We're searching for new physics, new sources of CP violation, and antimatter is one of the best places to look. Why? Because any difference in the behavior of matter and antimatter is a potential source of CP violation. If antihydrogen behaves even slightly differently from hydrogen, that could be the missing piece of the puzzle. So far, all measurements show perfect agreement, but precision grows every year, and someday. Let's take a break from deep physics and talk about something more tangible, about what happens during annihilation, step by step, atom by atom. Part 5. Anatomy of Annihilation. Imagine an electron, a tiny point of negative charge surrounded by a cloud of quantum probability. It moves, oscillates, exists in a superposition of countless states simultaneously. Now imagine a positron, identical to the electron in everything except charge, a positive point in the same kind of probability cloud. They approach each other, attracted to each other by electrostatic force. Opposite charges attract. That works here too. In the final nanoseconds before collision, something amazing happens. The electron and positron form a bound system, an atom-like structure where they orbit each other. This structure is called positronium. Positronium is an exotic atom, no nucleus, just an electron and positron dancing their final dance. Think of it as the universe's shortest-lived couple, doomed from the start, but beautiful while it lasts. The lifetime of positronium ranges from 120 picoseconds to 140 nanoseconds, depending on how the spins of the particles are oriented. The parameters of positronium agree with stunning precision with theoretical calculations from quantum electrodynamics. It's one of the best tests of our understanding of electromagnetic interaction at the quantum level. And then annihilation happens. The electron and positron merge. They don't collide, they don't shatter, they literally merge. Their masses, their charges, their spins, all of it converts to energy, to photons. How many photons? Depends on the spin orientation. If the spins are pointing opposite directions, singlet state, parapositronium, 2 photons are born. They fly in strictly opposite directions, each carrying energy of 511 kiloelectron volts. This is the energy corresponding to the electron's mass according to E equals mc squared. If the spins are parallel, triplet state, orthopositronium, 3 photons are born. They scatter in different directions, dividing the energy among themselves. Why the difference? Conservation laws. 2 photons can only have even spatial parity. 3 photons can have odd parity. Parapositronium has even parity. Orthopositronium has odd parity. Each must decay into a channel with matching parity. All this complexity happens in trillionths of a second, and the result? 2 or 3 gamma quanta flying at the speed of light, carrying energy that was just mass a moment ago. Now let's scale up. What happens when an antiproton annihilates with a proton? Here things get more complicated. A proton isn't an elementary particle. It's made of 3 quarks bound by gluons. An antiproton is made of 3 antiquarks. When a proton and antiproton approach each other, simple merging doesn't happen. The quarks and antiquarks begin interacting in complex ways. Quark-antiquark pairs annihilate, producing gluons. Gluons convert to new quark-antiquark pairs. This cascade happens inside a tiny volume, smaller than a femtometer, 10 to the minus 15th power meters. The result is a shower of particles, pions, kaons, eta mesons, sometimes heavier particles. All of this is unstable and quickly decays. Pions turn into muons and neutrinos. Muons turn into electrons, positrons, and neutrinos, and so on until only stable particles remain. Electrons, positrons, neutrinos, antineutrinos, and photons. About half the energy from proton-antiproton annihilation goes into neutrinos. Neutrinos barely interact with matter. They just fly off into space, carrying energy with them. This is important for understanding practical applications of antimatter. Not all its energy can be captured and used. But even accounting for neutrino losses, annihilation energy is colossal. 1 gram of antimatter annihilating with a gram of matter releases about 180 trillion joules. That's energy a typical power plant produces over several days. Now imagine a macroscopic amount of antimatter. Not a gram, but a kilogram, or a ton. A ton of antimatter meeting a ton of matter would release energy equivalent to approximately 40 million kilotons of TNT. That's roughly 800,000 Hiroshima-scale bombs. More than the entire nuclear arsenal ever created by humanity. 1 ton. No wonder the military takes an interest in antimatter. No wonder science fiction is full of antimatter bombs and engines. But reality, as always, is more complicated than fiction. Part 6. The Impossible Economics. Why antimatter costs more than the universe. Let's talk money. The biggest numbers you've ever seen in the context of something's cost. Antimatter is the most expensive substance known to humanity. And that's not an exaggeration. It's a literal fact. CERN, the world's largest particle physics laboratory, has produced approximately 20 nanograms of antihydrogen throughout its entire existence. 20 billionths of a gram. If you gathered all this antimatter into one point, which, by the way, is impossible, it was produced in portions of a few atoms and immediately used for experiments, you wouldn't see it with the naked eye. The cost of running CERN is about 1 billion euros per year. It's been operating since 1954. Yes, antihydrogen wasn't being produced that whole time, but let's simplify the calculation and imagine that roughly half the resources over the last 3 decades went toward antimatter experiments. That works out to something like 15 to 20 billion euros for 20 nanograms. That's about €1 trillion per gram. But even that's an optimistic estimate. It doesn't account for energy. To produce an antiparticle, you need to collide ordinary particles with enormous energy. This energy partially converts to the mass of antiparticles. E equals mc squared works both ways. But the process efficiency is negligible. For every antiproton produced, billions of protons are spent, along with corresponding amounts of energy. According to NASA calculations, producing 1 milligram of antimatter using current technology would require about 60 million gigawatt-hours of energy. That's humanity's annual energy consumption. And that's just for a milligram, a thousandth of a gram. If you want a gram of antimatter, you'd need the energy humanity produces over 1,000 years. At current electricity prices, that's equivalent to approximately $60 quadrillion, 60,000 trillion. For comparison, the entire world's GDP is about $100 trillion per year. Producing a gram of antimatter would cost more than 600 years of economic activity for the entire planet. This is why antimatter weapons aren't a military secret. They're an economic impossibility. This is why antimatter engines for spacecraft remain a dream. But wait, there's another problem, the storage problem. Let's say you somehow miraculously produced a gram of antimatter. Where do you keep it? In any container made of ordinary matter, antimatter will instantly annihilate. 1 gram would produce a 20 kiloton explosion. Your laboratory, your city, all gone. You need a magnetic trap, suspending antimatter in a vacuum using magnetic fields. But magnetic traps only work for charged particles. Antiprotons, sure. Positrons, sure. But neutral antihydrogen? Antihydrogen can be trapped because it has a magnetic moment. The electron-positron antiproton system in a bound state creates a weak magnetic field. This field interacts with an external, non-uniform magnetic field. If you configure the trap correctly, antihydrogen can be held. But this effect is weak, very weak. Current traps hold individual atoms of antihydrogen, not milligrams, not micrograms, atoms. To hold a gram of antihydrogen would require a trap of unimaginable complexity and energy consumption. Cryogenic magnets, ultra-high vacuum, stabilization systems, all would need to work flawlessly. The slightest failure, the slightest leak in the magnetic field, and a gram of antimatter touches the wall. Explosion. Storing antimatter isn't a technological problem. It's an existential problem. You're housing a doomsday device, and any failure means the end. This is exactly why all talk about antimatter bombs or antimatter fuel stays in the realm of science fiction. Not because physics doesn't allow it. Physics does. But engineering, economics, practical feasibility all say a firm no. At least with current technology levels. But what if technologies change? What if a new method of antimatter production is discovered, thousands of times more efficient? What if new storage methods emerge? That's not ruled out. Science doesn't stand still. What's impossible today may become reality in 100 years. Let's dream. Let's imagine a future where antimatter is available. Part 7. Dreams of an Antimatter Future. The year 2350. The orbital shipyard Prometheus orbits the Moon. In its docks, the interstellar ship Icarus is under construction, the first vessel that will leave the solar system with humans aboard. The heart of Icarus is an antimatter engine, not a super-efficient fusion reactor, not a solar-powered ion drive, not an exotic hyperdrive. Real technology, based on physics known since the 21st century. The ship's fuel, 10 grams of antihydrogen, stored in cryogenic magnetic traps. 10 grams, less than 2 teaspoons of sugar weigh. But these 10 grams carry energy equivalent to 20 megatons of TNT, enough to accelerate a 1,000-ton ship to 10% of the speed of light. The operating principle is elegant. Antihydrogen is gradually released from the traps and directed into an annihilation chamber. There it meets ordinary hydrogen. Annihilation. Some energy goes into neutrinos, but the rest goes into charged particles, pions and muons. A magnetic nozzle directs these particles backward, creating thrust. Mass to energy conversion efficiency, about 40%. The rest is lost to neutrinos. 40%? For comparison, chemical fuel converts about 1/1,000,000% of its mass to energy. Even fusion, less than 1%. At 10% of light speed, the journey to Proxima Centauri takes about 45 years. Add time for acceleration and deceleration, say 70 years one way. It's still a multi-generational mission, but now it's achievable. The first generation of astronauts departs. Their children arrive at the destination. This isn't fantasy. It's an engineering vision based on known physics. The problem isn't physics. The problem is producing and storing antimatter. But imagine those problems are solved. That somewhere in orbit, giant antimatter factories are operating. Solar collectors spanning thousands of square kilometers gather energy. Particle accelerators produce antiprotons. Cooling and recombination systems create antihydrogen. Magnetic containers store the finished fuel. This is possible. Not today, not tomorrow, but in principle, possible. Now let's imagine something more frightening. Antimatter weapons. In a world where antimatter is available, a bomb the size of an orange could carry the destructive power of a thermonuclear explosion. No critical mass, like with nuclear weapons, no complex implosion scheme, just a container of antimatter and a switch that turns off magnetic containment. The detonator could be radio-controlled, or timed, or triggered by detonating conventional explosives that destroy the magnet cooling system. A terrorist with an antimatter briefcase becomes a threat next to which nuclear terrorism looks like child's play. Fortunately, we're very far from such a future. Producing antimatter requires infrastructure on the scale of CERN. This isn't a basement laboratory. It's miles of accelerator tunnels, thousands of superconducting magnets, teams of engineers and scientists. But someday, technologies may simplify. And then humanity will have to address ethical questions we've barely begun to formulate. Okay, enough about the future. Let's return to the present. Because even today, antimatter does amazing things. Part 8. Antimatter in the hospital room. PET scanning. Let's talk about something that's already real. Technology that's saving lives right now as you're watching this video. Positron emission tomography, or PET scanning. PET scanning was developed in the 1970s. The first clinical applications began in the 1980s. Today, it's a routine procedure performed in thousands of hospitals around the world. The principle behind it is elegant, and it directly uses annihilation. Here's how it works. A patient receives an injection containing a radioactive isotope. Most commonly, it's fluorine-18, which is part of a compound called fluorodeoxyglucose, or FDG. Glucose is fuel for cells. Think of it as the gasoline your body runs on. Cancer cells consume glucose faster than normal cells. They're like gas-guzzling muscle cars compared to efficient hybrids. FDG looks like glucose to your cells, so they absorb it. But they can't actually metabolize it, so it just builds up inside them. Fluorine-18 is unstable. Its half-life is about 110 minutes. When the nucleus decays, it emits a positron. That positron travels a few millimeters through body tissue. Then it meets an electron. Annihilation. 2 gamma photons, each with an energy of 511 kiloelectron volts, fly off in exactly opposite directions. Around the patient is a ring of detectors. When 2 detectors on opposite sides of the ring register gamma photons simultaneously, within a few nanoseconds, the computer records an annihilation event. The line connecting these detectors passes through the point where annihilation occurred. Imagine it like this. If you heard two gunshots at exactly the same time from opposite ends of a hallway, you'd know the gun was fired somewhere in the middle of that hallway. Same principle, but with gamma rays. Millions of these events, registered during the scan, allow doctors to reconstruct a three-dimensional map of where the compound has accumulated in the body. Where there's a lot of it, bright spots on the image. Tumors, metastases, inflammatory processes. PET scanning revolutionized oncology. It allows doctors to detect cancer at early stages when the tumor is still too small for other imaging methods. It shows whether chemotherapy is working. A living tumor absorbs glucose, a dead one doesn't. It helps surgeons precisely define tumor boundaries before surgery. But oncology isn't the only application. Brain PET scans allow us to see neural activity in real time. Which areas of your brain are working when you're thinking, when you're remembering, when you're feeling emotions? PET shows this by tracking glucose consumption in different regions. This gave a huge boost to neuroscience. For the first time, we could literally watch the living brain work without opening up the skull. In Alzheimer's disease, amyloid plaques accumulate in the brain. Special PET compounds that bind to amyloid allow doctors to detect these plaques in living patients. This is critically important for early diagnosis and developing new treatments. In Parkinson's disease, dopaminergic neurons degenerate. PET with dopamine markers shows the extent of this degeneration. In epilepsy, PET helps locate the focus of seizure activity in the brain, critically important for planning surgical intervention. Cardiology uses PET too. Heart muscle consumes glucose. If part of the heart muscle is damaged by a heart attack, it stops lighting up on PET. This helps assess whether heart tissue is still viable and whether coronary bypass surgery would help. There's an irony here. Antimatter, a substance capable of destroying a city, is being used to save lives one at a time. The energy of annihilation, tamed and controlled, serves medicine. Every positron emitted inside a patient's body lives its tiny life, a millionth of a second, and then sacrifices itself along with an electron to give us information. Billions of such sacrifices in a single scan. Billions of microscopic annihilations in the name of diagnosis. It's strange and beautiful at the same time. Part 9. Antimatter in Space. Cosmic Ray Hunters. Let's look up at the stars, because out there, in the depths of space, there's antimatter too. And studying it is one of the most exciting frontiers of modern astrophysics. Cosmic rays are streams of high-energy particles bombarding Earth from all directions. Most of them are protons, but there are also helium nuclei, heavier nuclei, electrons, and antiparticles. Antiprotons in cosmic rays were discovered back in 1979. Positrons even earlier. Where do they come from? The main source is secondary production. Think of it like a cosmic game of billiards. When a cosmic ray proton collides with an atom of interstellar gas, a nuclear reaction occurs. Among the products of this reaction are particle-antiparticle pairs. Antiprotons and positrons born this way continue their journey through the galaxy until they reach Earth or annihilate with some atom along the way. But there's a mystery. Measurements show there are more positrons in cosmic rays than the secondary production model predicts, especially at high energies. Where are the extra positrons coming from? There are several hypotheses. First, pulsars. Rapidly spinning neutron stars with incredibly powerful magnetic fields. In the vicinity of pulsars, particles are accelerated to colossal energies, and under these conditions, electron-positron pairs are born. Pulsars might be natural positron factories. Second, dark matter annihilation. If dark matter consists of so-called WIMPs, weakly interacting massive particles, these particles could annihilate with each other, producing ordinary particles. Positrons could be a signature of this process. Third, some unknown astrophysical source we don't know about yet. To solve this mystery, the AMS-02 experiment, Alpha Magnetic Spectrometer, was created. This is a particle detector costing about $2 billion, installed on the International Space Station in 2011. AMS-02 is the most complex and sensitive cosmic ray detector ever built. It registers millions of particles every day, measuring their charge, mass, energy, and direction of arrival. The results from AMS-02 confirm the positron excess. Measurements are becoming more precise, but there's no definitive answer about the source yet. Both pulsars and dark matter remain possible explanations. If the source is dark matter, that would be an incredible discovery. The first direct detection of dark matter particles through the products of their annihilation. A guaranteed Nobel Prize. A revolution in physics. But proving it is difficult. You need to rule out all alternative explanations. You need more precise measurements. You need new experiments. There's another intriguing question. Are there regions in the universe made of antimatter? We discussed this earlier. If such regions existed, at their boundaries with regions of ordinary matter, annihilation would occur, producing characteristic gamma radiation. We don't see such radiation, so if antimatter regions exist, they must be very far away. How far? Estimates show at least several hundred megaparsecs. That's comparable to the size of the observable universe. There's practically no chance that large antimatter structures exist in our cosmic neighborhood. But maybe there's something smaller. Antistars? In 2021, an analysis of data from the Fermi Gamma Ray Space Telescope was published. Researchers were looking for objects whose gamma spectrum would correspond to annihilation on the surface of an antistar accreting ordinary interstellar matter. They found 14 candidates. This doesn't mean antistars have been discovered. It means there are 14 gamma ray sources that can't be explained by known mechanisms. Antistars are one possible explanation, but there are others. If even one of these candidates turns out to be a real antistar, it would overturn everything we know about baryon asymmetry. If antistars can exist in our galaxy, then the asymmetry isn't so complete after all. Somewhere in the early universe, antimatter could have become isolated from matter and survived. But for now, this is speculation. More observations are needed. Time is needed. Part 10. The Great Experiments. CERN and the Hunt for Asymmetry. We've already mentioned CERN and experiments with antimatter. Let's dive deeper. Because what's happening in these laboratories is the cutting edge of human knowledge. ALPHA, Antihydrogen Laser Physics Apparatus, is the flagship experiment for studying antihydrogen. We already talked about how ALPHA traps antihydrogen and measures its spectrum. But that's only part of the story. In 2020, ALPHA announced the first measurement of the Lamb shift in antihydrogen. The Lamb shift is a subtle effect in an atom spectrum related to quantum fluctuations of the electromagnetic field. Its discovery in ordinary hydrogen in 1947 was an important milestone in the development of quantum electrodynamics. Willis Lamb received the Nobel Prize for it. Measuring the Lamb shift in antihydrogen is a test of CPT symmetry at an even finer level. The result? Agreement with hydrogen within experimental error. CPT symmetry held up again. ASYCUSA, atomic spectroscopy and collisions using slow antiprotons, is another experiment working with antimatter. Its specialty is creating beams of antihydrogen that can be studied in flight, outside a trap. This opens new possibilities for spectroscopic measurements. ASYCUSA also studies exotic atoms. Atoms where one of the usual components is replaced by an antiparticle. For example, antiprotonic helium, a helium atom where one electron is replaced by an antiproton. The properties of such systems allow for highly precise measurements of the antiproton's mass and searches for CPT symmetry violations. BASE, Baryon-Antibaryon Symmetry Experiment, focuses on precision measurements of the properties of individual antiprotons. In 2017, BASE measured the magnetic moment of the antiproton with record precision, 1.5 parts per million. The result matched the proton's magnetic moment. That's incredible precision. It's like measuring the distance from Earth to the Sun with an error of just a few inches. G-bar, gravitational behavior of antihydrogen at rest, is a newer experiment aimed at measuring the gravitational acceleration of antimatter. We mentioned it earlier. The idea? Cool antihydrogen to ultra-low temperatures, microkelvin range, and observe its freefall. AEGIS, antihydrogen experiment, gravity, interferometry, spectroscopy, is another experiment studying antimatter gravity. The method is different. Here, interferometry is used to measure acceleration. All these experiments share one goal: find any difference between matter and antimatter, any tiny crack in the mirror symmetry. Because that crack is the key to understanding why the universe exists. So far, no crack has been found. Antimatter stubbornly obeys all known symmetries, but measurement precision grows every year, and the space where new physics could be hiding is steadily shrinking. Part 11. Theoretical Frontiers. Where is new physics hiding? If experiments aren't finding symmetry violations, maybe we need new theories? New ideas about where to look? Theoretical physics isn't sitting idle. There are many hypotheses trying to explain the baryon asymmetry of the universe. Leptogenesis. The idea is that asymmetry first arose not between baryons and antibaryons, but between leptons and antileptons. Leptons are electrons, muons, tau leptons, and neutrinos. This leptonic asymmetry was then converted into baryonic asymmetry through Sphaleron processes in the early universe. The key element of leptogenesis is heavy neutrinos. The standard model doesn't include a mechanism explaining neutrino mass, but we know neutrinos have mass. Neutrino oscillations prove this. There are theories introducing additional very heavy neutrinos. These heavy neutrinos, decaying in the early universe, could have created leptonic asymmetry with sufficient CP violation. Electroweak baryogenesis. This idea is connected to the electroweak phase transition, the moment in the early universe when electromagnetic and weak interactions separated. If this transition was sharp enough, first order, as physicists say, it could have created conditions for generating baryonic asymmetry. The problem, in the standard model, the electroweak transition is too smooth. New physics is needed, additional scalar fields, extensions of the Higgs boson, to make the transition sharp enough. Affleck-Dine baryogenesis, a mechanism arising in supersymmetric theories. Certain scalar fields, directions in configuration space, called flat directions, can acquire large values in the early universe. When these fields begin to oscillate and decay, they produce baryonic asymmetry. Gravitational baryogenesis. The idea of linking baryonic asymmetry to the expansion of the universe. In expanding spacetime, effective CP violation can arise even if symmetry is exact at the microscopic level. These are just some of the many theoretical scenarios. Each has its own predictions that can be tested experimentally. The search continues at accelerators, in neutrino experiments, in astrophysical observations. There's one more direction that deserves its own discussion. Part 12. Antimatter and dark matter. Two mysteries, one universe. Baryon asymmetry isn't the only cosmological puzzle. There's also dark matter and dark energy. Three great mysteries of modern cosmology. Strangely, baryon asymmetry and dark matter might be connected. Here's an amazing observation. The amount of dark matter in the universe is roughly 5 times greater than the amount of ordinary matter. 5 to 1. This ratio could have been anything. 1,000,000 times more, 1,000,000 times less. But it's on the order of 1. Why? This is called the coincidence problem. If dark matter and ordinary matter have completely different origins, why are their amounts so close? Think of it this way. If I told you I have some apples and some oranges, and I asked you to guess how many oranges I have for every apple, you'd probably guess something random, maybe 100 oranges per apple, or 1 orange for every 1,000 apples. The last thing you'd expect is that they're roughly equal. But that's exactly what we see with dark and ordinary matter. There are theories trying to explain this coincidence through common origin. Asymmetric dark matter is one such theory. The idea? Dark matter, like ordinary matter, has its own asymmetry. There are dark particles and dark antiparticles. In the early universe, an asymmetry arose, an excess of dark particles over dark antiparticles. And the mechanism that created this asymmetry is connected to the mechanism that created baryonic asymmetry. If the mass of the dark matter particle is chosen correctly, roughly 5 times the proton mass, the ratio of dark to ordinary matter densities comes out to exactly what we observe. It's elegant. One mystery explains another, but for now, it's just a hypothesis. There's no proof. Dark matter particles haven't been detected in any experiment. We know dark matter exists only from its gravitational influence on galaxies and the large-scale structure of the universe. The search for dark matter is one of the most important directions in modern physics. Detectors located deep underground search for rare collisions of dark matter particles with ordinary atoms. Accelerators try to produce dark matter particles in collisions. Space telescopes look for signals from dark matter annihilation. And here antimatter appears again. Because if dark matter annihilates, the products of annihilation could be positrons and antiprotons. Those same excess positrons that AMSO2 sees could be a signal from dark matter. Two mysteries woven together, antimatter and dark matter. Perhaps the key to both lies in understanding the early universe. In those first moments after the Big Bang, when all the asymmetries were laid down that determine the fate of the cosmos. Part 13. The Big Bang, when everything was different. Let's take a journey into the past, to the very beginning, to that moment when time itself had barely begun. 13,800,000,000 years ago, the Big Bang. No, it wasn't an explosion in the usual sense, not something exploding into empty space. It was the expansion of space-time itself from a state of unimaginable density and temperature. In the first Planck unit of time, 10 to the minus 43rd power of a second, the temperature of the universe was approximately 10 to the 32nd power Kelvin. The laws of physics as we know them don't work there. Quantum gravity, strings, loop quantum gravity, these are all just theories trying to describe this regime. By the time 1/billionth of a second had passed, the temperature dropped to about 10 to the 13th power Kelvin, 1,000,000,000,000 degrees. Now we're in territory described by the Standard Model. In this infernal cauldron, all known particles were constantly being born and annihilating. Quarks and antiquarks, electrons and positrons, neutrinos and antineutrinos, gluons and photons, W and Z bosons, even Higgs bosons. Imagine the most crowded New Year's Eve party ever, but instead of people, it's particles, all bumping into each other billions of times per second, constantly appearing and disappearing. Everything was in thermal equilibrium. Birth and destruction were balanced. The number of particles was determined by temperature, according to statistical laws. The universe expands. Temperature drops. At a temperature of about 10 to the 12th power Kelvin, the electroweak phase transition occurs. The unified electroweak interaction separates into electromagnetic and weak forces. W and Z bosons acquire mass. Particles begin to feel Higgs mass. Somewhere here, according to many theorists, baryonic asymmetry should have arisen. The details are unknown, but the general picture is clear. Some process related to this transition created a small excess of quarks over antiquarks. At a temperature of about 200 megaelectron volts, roughly 2 trillion Kelvin, quark-gluon confinement occurs. Quarks and gluons, previously flying freely in the hot plasma, bind into hadrons, protons, neutrons, mesons. This is where antiquarks meet their fate. Practically all antiquarks annihilate with quarks. Only a small excess remains, roughly 1 quark for every billion pairs. These remaining quarks form protons and neutrons. Why was there this excess? We don't know exactly, but without it, we wouldn't exist. At a temperature of about 1,000,000 Kelvin, a few seconds after the Big Bang, electron-positron annihilation occurs. Again, almost complete. A small excess of electrons over positrons ensures the universe's electrical neutrality. By 3 minutes after the Big Bang, the temperature drops enough for nucleosynthesis to begin, the synthesis of light nuclei. Protons and neutrons combine into nuclei of deuterium, helium, small amounts of lithium. 400,000 years later, the temperature drops to a few thousand Kelvin. Electrons are captured by nuclei, forming neutral atoms. The universe becomes transparent to light. The cosmic microwave background radiation, the same radiation we observe today, is released. This background carries information about the state of the universe at that moment. And one of the things it tells us is confirmation of baryonic asymmetry. Analysis of the cosmic microwave background allows us to estimate the ratio of baryons to photons, approximately 6 times 10 to the minus 10th power. This number, 6 billionths, is the measure of baryonic asymmetry. It captures the result of everything that happened in those first moments, and it remains a mystery. Part 14. Fermions, bosons, and their shadows. Let's dive deeper into the structure of matter and antimatter. Because the differences and symmetries here are surprisingly rich and subtle. All particles are divided into two major classes, fermions and bosons. Fermions have half-integer spin, 1/2, 3/2, and 3/2. Bosons have integer spin, 0, 1, 2, and 3/2. Fermions obey the Pauli exclusion principle. Two identical particles cannot occupy the same quantum state. Think of it like assigned seating at a concert. Each electron gets its own seat and no sharing allowed. This explains why electrons in an atom occupy different orbitals, why chemical elements exist, why matter doesn't collapse into a point. Bosons don't obey the Pauli principle. They can pile up in the same state, like a mosh pit at a rock concert where everyone can occupy the same space. This explains superfluidity, superconductivity, the existence of laser light. Every fermion has its antiparticle. Quarks, antiquarks. Electrons, positrons. Neutrinos, antineutrinos. With bosons, it's more complicated. Some bosons are their own antiparticles. The photon is the antiparticle of itself. The Higgs boson is the antiparticle of itself. The graviton, if it exists, is the antiparticle of itself. Gluons, too. Although gluons carry so-called color, the quantum number of strong interaction, a gluon is its own antiparticle in a certain sense. W bosons have antiparticles. W plus and W minus are antiparticles of each other. The Z boson is its own antiparticle. Question: can a fermion be its own antiparticle? For charged particles, no. The electron has charge -1. Its antiparticle must have charge +1. These are different particles. But what about neutral particles? Neutrinos, for example. Here begins one of the most interesting puzzles in modern physics. The neutrino is a neutral particle. The neutrino has no electric charge. The neutrino doesn't participate in strong interactions. What distinguishes a neutrino from an antineutrino? In the Standard Model, the answer is related to helicity, the projection of spin onto the direction of motion. Neutrinos are always left-handed, spin directed against motion. Antineutrinos are always right-handed, spin directed along motion. But this situation may be a consequence of neutrinos being massless particles in the Standard Model. And we know that neutrinos have mass. If neutrinos are massive, we can ask, are neutrinos and antineutrinos different particles? Or are they the same particle, just in different states? If they're different, the neutrino is called a Dirac particle, like the electron. If they're the same, the neutrino is called a Majorana particle. Ettore Majorana, a mysterious Italian physicist who disappeared under mysterious circumstances in 1938, proposed that fermions could exist that are their own antiparticles. The Majorana equation describes such particles. If neutrinos are Majorana particles, this has profound consequences. It would explain the mechanism for neutrino mass generation, the so-called seesaw mechanism. It would open the door to leptogenesis, explaining baryonic asymmetry through leptonic asymmetry. And it would allow a process called neutrinoless double beta decay. Ordinary double beta decay is when a nucleus emits 2 electrons and 2 antineutrinos, transforming into a nucleus with a charge 2 units higher. This is an ordinary process observed for some isotopes. Neutrinoless double beta decay is when a nucleus emits only 2 electrons, without neutrinos. This is possible only if neutrinos are Majorana particles. The antineutrino from one decay is absorbed as a neutrino in the second decay. Many experiments around the world are searching for neutrinoless double beta decay. They haven't found it yet, but the search continues because the stakes are high. If neutrinos are Majorana particles, it overturns our understanding of matter and antimatter. It means the boundary between them is more blurred than we thought. Part 15. Antiparticles in the periodic table. Let's come down from the heights of theoretical physics and talk about chemistry. Anti-chemistry, if you will. The antihydrogen atom is the simplest anti-atom. 1 antiproton, 1 positron. We know how to create it, trap it, study it. But what about more complex anti-atoms? Anti-helium, anti-carbon. Theoretically, they should exist and behave exactly like ordinary atoms. The anti-periodic table would look identical to the regular one. Anti-oxygen would have the same chemical properties as oxygen. Anti-water would freeze at 0 degrees Celsius. Anti-life could exist and develop according to the same laws of biology. Practically, we're very far from creating complex anti-atoms. In 1965, at the Brookhaven Accelerator, antideuterium was discovered, nuclei consisting of an antiproton and an antineutron. This was the first antinucleus more complex than an antiproton. In the 1970s, anti-helium-3 nuclei were synthesized, 1 antiproton and 2 antineutrons. In 2011, at the RHIC Collider, Relativistic Heavy Ion Collider, anti-helium-4 nuclei were discovered, 2 antiprotons and 2 antineutrons, a complete anti-helium nucleus. These are the heaviest antinuclei created on Earth. Creating heavier ones requires even greater energies and even rarer coincidences in collisions. Anti-atoms, atoms with a nucleus and positron shells, have been created only for hydrogen. An anti-helium atom, anti-alpha particle plus 2 positrons, has never been synthesized. It's technically possible, but incredibly difficult. And here an interesting question arises. Does anti-chemistry differ from ordinary chemistry? The CPT theorem says it shouldn't. Atomic energy levels are determined by electromagnetic interaction. Electromagnetic interaction preserves CPT symmetry. Therefore, the energy levels of an antiatom are identical to the levels of an atom. Chemical reactions are determined by the distribution of electrons across levels. If the levels are identical, the reactions are identical. Anti-water, H2O, should have the same properties as water, the same melting and boiling points, the same heat capacity, the same ability to dissolve substances. Antiproteins should fold the same way as ordinary proteins. Anti-DNA should store information the same way as ordinary DNA. Anti-life, if it arose, wouldn't differ from ordinary life in anything except one fatal property. It couldn't coexist with us. Imagine a meeting of 2 civilizations, one made of matter, the other of antimatter. They can't shake hands. They can't exchange physical artifacts. Any contact means annihilation, explosion, death. This is a favorite science fiction plot. But let's think more seriously. If an anti-civilization existed in the universe, how would we know? Their radio signals would be identical to ours. Photons have no antiparticles. They're the same for matter and antimatter. Their stars would shine the same way. Their planets would reflect light the same way. The only way to know is direct contact. Send a probe, or receive their probe. And here's where drama begins. How do you tell whether an approaching alien spacecraft is made of matter or antimatter? Before it enters our atmosphere and causes a planetary scale catastrophe? There are ways. You could send a tiny probe to intercept it. If it annihilates, answer clear. You could analyze particles emitted by the ship's engines. If there are positrons instead of electrons, alarm. But this is pure speculation. Let's return to real science. Anti-chemistry as a discipline doesn't exist yet. We don't have enough antimatter to conduct chemical experiments. But everything we know about physics says anti-chemistry would be identical to chemistry. This is yet another confirmation of the universe's deep symmetry. A symmetry that makes the mystery of baryonic asymmetry even more acute. Part 16. Philosophy of the Mirror. What antimatter tells us about the nature of reality. Let's step back from physics for a moment and talk about philosophy. Because antimatter poses questions that go beyond science. What is existence? Matter exists. We know this because we ourselves are made of matter. We interact with matter. We measure matter. But antimatter also exists. We create it. We measure it. We observe its annihilation. Does antimatter exist the same way as matter? Or is its existence somehow less real because there's so little of it in the universe? Physics says there's no difference. Antimatter is just as real as matter. The laws of physics treat it just as seriously. It's just rare, a statistical accident of the early universe. But this raises another question. If antimatter is just as real, why did matter win? Is there something special about matter? Or is it pure chance? Some physicists suggest that our distinction between matter and antimatter is just a convention. We call matter what we're made of. If we were made of antimatter, we'd call it matter and call current matter antimatter. It's like left and right. There's nothing objectively left in the universe. It's just a way to distinguish two directions. Similarly, there's nothing objectively material. It's just a way to distinguish two types of substance. But then, why did one type win? Why wasn't there perfect balance? The CPT theorem says the laws of physics don't distinguish matter and antimatter directly. They distinguish them only in combination with space reflection and time reversal. Maybe the key is in time? There's a radical hypothesis, proposed by several physicists, including Richard Feynman. An antiparticle is a particle traveling backward in time. A positron is an electron traveling from the future into the past. Sounds crazy? Let's break it down. In quantum field theory, antiparticles are mathematically described as particles with negative energy traveling backward in time. This isn't a metaphor. It's literally what the equations say. When an electron and positron annihilate, from a mathematical point of view, you can interpret it this way. The electron emits a photon and reverses direction in time, becoming a positron going into the past. Feynman diagrams, the graphical language for describing particle interactions, don't distinguish between a particle going forward and an antiparticle going backward. It's the same line, just with different arrows. Of course, this is only a mathematical description. We can't send a message into the past via positrons. Causality is preserved. But the very possibility of such an interpretation speaks to a deep connection between antimatter and the nature of time. If antimatter is matter going backward in time, then baryonic asymmetry is an asymmetry in time. Why does the universe prefer one direction of time over another? This connects to the second great asymmetry, the arrow of time. Why does entropy increase? Why do we remember the past but not the future? Why does an egg break but not unbreak? Physicists still debate the nature of the arrow of time. Some consider it fundamental, built into the laws of physics. Others see it as a consequence of initial conditions, the low entropy of the Big Bang. Antimatter is a window into these deep questions. Every experiment with antimatter is an investigation into the nature of time, causality, the very structure of reality. Part 17. Antimatter in Culture. From Star Trek to Angels and Demons. Antimatter has long captured the imagination of writers and filmmakers. It's appeared in science fiction since the 1950s, and its popularity only grows. Star Trek is probably the most famous example. The Starship Enterprise is powered by a warp drive running on matter-antimatter reaction. Dilithium crystals regulate the annihilation. If something goes wrong with the antimatter containment system, catastrophe. This plot device has been used dozens of times. How realistic is this? The warp drive is pure fantasy. Warping space-time for faster-than-light travel requires exotic matter with negative energy density. Antimatter has positive energy density. It won't help. But an antimatter engine for sublight speeds, that's a real concept. NASA has funded research on this topic. The basic idea is exactly like in Star Trek: controlled annihilation, converting energy into thrust. The problem, as we discussed, is production and storage. The Enterprise carries tons of antimatter on board. With current technology, producing that amount would require more energy than all of human civilization has generated throughout history. Angels and Demons by Dan Brown is another famous example. In the novel, terrorists steal 1/4 gram of antimatter from CERN and threaten to blow up the Vatican. How realistic is this? CERN does produce antimatter, but not 1/4 gram. In all its years of operation, nanograms, billionths of a gram. Producing 1/4 gram would take thousands of years at current capacity and storage. In the novel, antimatter is stored in a portable container the size of a jar. In reality, magnetic traps for antimatter are extremely complex installations with cryogenic systems, vacuum chambers, and powerful magnets. You can't carry them in a backpack. But as a plot element, it works. The film came out in 2009, and CERN collaborated with the creators, explaining the real science. This brought enormous attention to antimatter research. Futurama uses antimatter for comedy. In one episode, a ship from the antimatter universe appears. It's identical to a regular ship, but everything is opposite, including a goatee on Mirror Universe Fry. It's a joke, but it accurately reflects physics. An anti-universe really would be a mirror reflection of ours, if it existed. Video games don't ignore antimatter either. In the Mass Effect series, antimatter is used as fuel for engines and weapons. In StarCraft, the Protoss have antimatter missiles. In Half-Life, you can find antimatter traps. Science fiction does important work. It introduces the general public to concepts that would otherwise remain the domain of specialists. Yes, the details are often inaccurate, but the general idea that antimatter exists, that it's powerful, that it's dangerous, penetrates mass consciousness. And sometimes it inspires future scientists. How many physicists started their journey after watching Star Trek? How many engineers dream of building an antimatter engine? Culture and science feed each other. Antimatter is a beautiful example of this symbiosis. Part 18. Open Questions. What we still don't know. We've come a long way, from Dirac's theoretical prediction to CERN experiments, from annihilation to cosmology. But science never ends. There are always questions without answers. Let's gather the main antimatter mysteries that remain unsolved. First mystery: why is there more matter than antimatter? This is the main question. We discussed it in detail. Sakharov conditions, CP violation, leptogenesis, electroweak baryogenesis. Many theories, none confirmed definitively. What's needed for an answer? New experiments, more precise measurements of CP violation, search for new particles, detection of neutrinoless double beta decay, perhaps discoveries at future colliders. Second mystery, is there antimatter in space? We don't see anti-galaxies. We don't see anti-stars. But there are candidates, mysterious gamma-ray sources that could be anti-stars. AMS-02 on the ISS continues collecting data. Maybe someday it will register an anti-helium nucleus of cosmic origin. That would be a sensation. Proof that somewhere in the universe, regions of antimatter have survived. Third mystery. Does antimatter fall up or down? Experiments in 2023 showed that antihydrogen falls down, like ordinary matter. Anti-gravity is ruled out, but measurement precision is still limited. Perhaps antimatter falls slightly slower, by fractions of a percent. That would indicate new physics. Experiments continue. G-bar, Aegis. Precision grows every year. Fourth mystery. Are there differences in the properties of matter and antimatter we haven't discovered yet? All measured properties, mass, charge, magnetic moment, spectrum, match. But we haven't measured everything. There are properties not yet tested with sufficient precision. For example, interaction with the weak force. CP violation in weak decays is known, but the complete picture isn't established. Perhaps there are additional sources of CP violation that manifest differently in antimatter. Fifth mystery. Do Majorana fermions exist? Neutrinos might be their own antiparticles. This would radically change our understanding of matter and antimatter. Experiments have been searching for neutrinoless double beta decay for decades. So far, nothing. But sensitivity grows. Sixth mystery. What role does antimatter play in the dark sector? Is baryonic asymmetry connected to dark matter? Does dark antimatter exist? These questions lie at the intersection of cosmology's two greatest mysteries. Seventh mystery. Can we ever use antimatter practically? For medicine, already yes, PT scanning. But for energy? For space travel? That requires breakthroughs in production and storage that aren't yet visible on the horizon. Science is a journey without end. Every answer generates new questions. Antimatter is a beautiful example of this endless search. Part 19. The future of research. What's next? Let's look into the future. What experiments are planned? What technologies are being developed? What can we expect in the coming decades? CERN continues its work. The anti-proton decelerator and ELENA will operate for many more years. The alpha, base, G-bar, and Aegis experiments are becoming increasingly precise. By 2030, the precision of antimatter gravitational acceleration measurements could reach fractions of a percent. New accelerators. Plans are being discussed for building the Future Circular Collider, FCC, a collider with a 100-kilometer circumference, 4 times larger than the Large Hadron Collider. It will be able to produce antiparticles with unprecedented intensity and study their properties with new precision. Space experiments. AMS-02 will continue operating on the ISS at least until 2030. New cosmic ray detectors with even greater sensitivity to antiparticles may be launched. Neutrino experiments. Projects like LEGEND, NEXO, and others will search for neutrinoless double beta decay with sensitivity sufficient to test many theoretical models. Storage technology. New types of magnetic traps are being researched. Superconducting magnets are becoming more powerful and compact. Perhaps in a few decades, portable devices for storing small amounts of antimatter will appear. Antimatter production. The biggest bottleneck. Current methods are incredibly inefficient, but alternatives are being researched. Laser production of antimatter, using ultra-powerful lasers to create electron-positron pairs in vacuum. Theoretically possible, practically at the edge of current technology. Medical applications. PET scanning will continue developing. More sensitive detectors. New radiopharmaceuticals. Possibly therapeutic use of antimatter. Research exists on using antiprotons for cancer treatment. An antiproton stopping in a tumor annihilates and destroys cancer cells around it. Theoretical breakthroughs. Perhaps someone will devise a new theory unifying known facts and predicting new phenomena. Like Dirac in 1928. Theoretical physics isn't standing still. The future is unpredictable. The greatest discoveries often come from where they weren't expected. Maybe the next breakthrough in understanding antimatter will happen tomorrow. Maybe in 100 years. But it will happen. Humanity won't stop asking questions. Part 20. Finale. We, children of asymmetry. We've reached the end of our journey. But before we finish, let's stop and reflect on what we've learned. Antimatter isn't just an exotic substance. It's a mirror reflecting the deepest structure of reality. In this mirror, we see symmetry, almost perfect symmetry between matter and antimatter. Masses match. Charges are opposite but equal in magnitude. Spectra are identical. The laws of physics treat matter and antimatter equally. Almost. And in that almost lies everything. Because if symmetry were perfect, we wouldn't exist. There would be no stars, planets, life, consciousness. Only cold, empty space filled with residual radiation from ancient annihilation. We exist because of a tiny crack in the symmetry. 1 particle in a billion. A negligible asymmetry that gave birth to everything that exists. In a sense, we are children of this asymmetry. Descendants of that small victory of matter over antimatter. Heirs of cosmic chance. Or not chance. Here's the main question antimatter leaves us with. Was the asymmetry inevitable? Is it written into the laws of physics at some deep level? Or is it truly random, a quantum fluctuation that could have gone differently? If the laws of physics are symmetric and initial conditions are random, then other universes exist where antimatter won. Universes populated by anti-beings who call their substance matter and wonder where the antimatter went. But if asymmetry is written into the laws, then there's something special about our type of substance. Something that makes it more stable, more probable, more real in some deep sense. We don't know the answer. Yet. But we're searching. Every experiment at CERN, every observation of cosmic rays, every refinement of theoretical models, all of these are steps on the path to an answer. And someday we'll know. We'll know why the universe is the way it is, why we exist, why there's something rather than nothing. Antimatter is a key, one of the keys, to the greatest mystery humanity has ever posed, the mystery of our own existence. We began this journey with a simple fact. Right now, inside your body, antimatter is being born. Positrons emitted by potassium atoms. Tiny flashes of annihilation happening millions of times per minute. Now you know what this means. You carry within you echoes of that ancient war between matter and antimatter. You are living proof of matter's victory. You are the embodiment of cosmic asymmetry. And every time you look at the stars, remember, all of this, from the smallest atom to the greatest galaxy, exists only because once, 14 billion years ago, the balance shifted ever so slightly in our favor. 1 in a billion. That was enough.